So I start. Okay, and the name of my institution, CESBIO, where also many of us during the course are coming from also. Okay, the contents of the talk, there's 5 things: the introduction, and then some detail on the statistical properties of the SAR images, and the physical content of SAR data. So I separated the images and the information of the data, the SAR information. And then some application to agriculture and to forest with biomass estimation to repeat or complete Glimmer excellent presentation. Okay, the first thing is the SAR mission. A SAR mission orbit over the Earth and sending and transmitting radar wave, and usually it's carry a synthetic antenna to generate a wave to the Earth. And the radar working in the part of the electromagnetic spectrum, which is the radar or microwave part. And here you see here a small part here around 1 centimeters to 1 meters is bigger than that for the P-band. And then if I compare to here the thermal infrared and visible and near infrared, it's optical, infrared, and the SAR. So the spectral bands here, and here we are very familiar to the optical remote sensing using the visible and near infrared wavelength. Here we have the all-weather observing system. Here we look at the forest in Cameroon with Sentinel-1 and Sentinel-2. And then many days, we just see the cloud with the Sentinel-2, and with Sentinel-1, we follow the deforestation in this part. Here you see the Sentinel-1 with the very dense tropical forest. Okay, so can I have 1 minute to look at the PowerPoint? This is, you see my screen, okay? Okay, so sorry. The this one shows the atmospheric effect, and I don't talk about cloud, I don't talk about rain, because it's obvious that in case of rain and cloud, we cannot see through the cloud with optical data. But what about the atmospheric constituent? Atmospheric constituent, water vapor, oxygen, etc. And here you can see here attenuation versus frequency or wavelength. So the attenuation, low attenuation, open 1, and strong attenuation is 1000. And here you go from sub-millimeter wave, millimeter wave, and microwave here. And the where you go from the we'll see later X, C, S, N, and P-band. The attenuation here is very low, starting say 5 centimeters. Starting C-band is 10 centimeters, and for P-band at 7 centimeters is quite low. Otherwise, at X-band, for example, here at 3 centimeters, you can have some problem of water or drop of rain, etc. And you don't have it at a lower frequency or longer wavelength. And the imaging SAR. We have a system going, orbiting the Earth and transmitting the wave. And this is an active system. You can have day and night operation, and the system receives back the transmitted wave, and then from this, okay, from this echo, that's why the lectures called echo from space. From the echo, you derive all the information concerning the target. And here, this show the side-looking radar with an antenna, and in azimuth direction, range direction, there's a pulse transmit to here the target, and the antenna displays linearly along the track, is along the orbit. And so there's two information. The range information come from the time need to the pulse to travel to the target and then back. And then there's the azimuth direction, and come from the displacement of the antenna. And then why the side looking? Where the side looking? As we say, we have here airborne system, and here a radar transmitting a beam. And when you have here 2 points in the earth that they have been looking at exactly the same time, the beam, the wave arrive at those 2 points at the same time. And if you want to detect the echo from this one and this one, using the time difference or the range difference, you cannot. They will arrive simultaneously. And if you do the side-looking radar here, the wave will go that way. And if you want to look at this one, and then here the you have a different time for different point on the earth, and different time here that help you to detect to recognize that this one come to that one on the earth. And so to detect the differences in time and the difference in range, and then to assign the point to the earth. And with the theory of radar antenna, here you have this is the antenna, the length is L, and you have the aperture, angular aperture of the antenna, theta, and the theta is given by this formula, wavelength over the antenna length in this horizontal direction. So meaning that when the length is very long, the resolution, the antenna angular aperture is small when the antenna is very long. And also it depends on the wavelength. When you have a 3 centimeter wavelength or 1 meter wavelength, it's the factor, the resolution is different. And the larger the antenna, the narrower the aperture. And in order to have the fine resolution here, resolution R equal to theta multiplied by R. R is the distance here. And if you see the resolution here is lambda multiplied by R divided by L here, lambda over L. And so if you have antenna 10 meters and the distance 1,000 kilometers, and for the C-band, and then the resolution will be 5 kilometers. It's two course, 5 kilometer resolution. And the synthetic aperture techniques is to use the displacement of the radar, and to simulate an array of antenna, and then moving along the flight line, this line NS. And okay, if one point on the Earth is a P, and when the antenna is at the place X1, then we start to have the signal from the radar, the signal at the P. And if the antenna move at X2, Xn, etc., and each time the P band is seen by the antenna. And so if all the signal from all the virtual antenna are coherently recorded and added together, and then also the target assumed to be static during the period, if the target should not be moved during the period of a fraction of second. And then we simulate a large antenna having the here the distance of the from the X1 to Xn is the equivalent of a virtual antenna LS, and so the azimuthal resolution is a lambda L over LS. So the NS could be very large, so you can have a good resolution in azimuth direction. So it says the principle of synthetic aperture radar. And then here the satellite orbit here, the radar look angle going like this, and the slant range is the range in side looking, and here is the crow range, here. And when the radar displays along the orbit, it creates an image in azimuth direction, and here is the range direction, and here's the antenna footprint. And what the SAR is measuring, here the wave going here with a cycle, and the wavelength is materialized here, and the phase from here to here, the phase. And here we have the amplitude A from the max to the mean here, and the phase is a part of 0, 2 pi, 4 pi, and etc. And the amplitude depends on the target properties, dielectric and geometric properties, and the phase is a function of the sensor target distance and the target properties as well. And so we can measure the amplitude, the phase, and we can also measure the time of the different signal, like the radar of police for the car, for example. And so we have the amplitude, and our intensity is amplitude squared. And you have the phase, and usually we call intensity or power and the phase. And then we have own kind of measurement, like here the SAR measurement mode. Here is on biomass that Clément have talked about. Here is the polarimetric SAR, one single image with polarimetry. Here, two images acquired with two orbit or baseline. And here, the multiple baseline allowing to take the tomography of the target. So there's one single SAR a pair of SAR images, and here is the multiple acquisition with different orbit with small replacement of the orbit. And so you see that you check for one image intensity or amplitude in the phase, and then you take the different image using different orbits for SAR and SAR. And if you take one image, the polarimetric image, it's the phase of one image, exactly one image, one polarization is not useful. You cannot use it. Let's see why. And then here we talk about the possibility to use different images from different acquisition. Here the SAR that you will see a lot during this week. It's just that something that we saw in the land forest times ago. And here the principle is at one of the polarization. You see here the distribution of the signal as Raymond have shown, and HH, VV, HV with the same trees. And so, and here with the phase center height here for HV, VV, and HH. And with the, in this case, when we do the some modeling here with the random volume of overcrowd, for example, for this kind of forest, we could retrieve the tree height with some uncertainty. But it's a way to use a different mode in order to have more information. And this is also the earlier example of using radar interferometry to have the terrain relief, here the iso-altitude curve of the Etna, and then to have the terrain displacement here with the fringe, and in order to have a cartography of terrain displacement, like here the basement of the volcano. And here just the example of the interferogram, which show that you can use, here is a 1 ERS intensity image, and here is a pair of images which show here something like a man here, but it show boundaries between the US and Mexico. But guess where is the US and where is Mexico? It's the US here, Mexico here, and here here is the thermal geothermal plant, and that they pump the water here to irrigate the field. And so here in the Mexico part, there is the fringes, and to show the crowd subsidence around the plant. Okay, the subsidence of about 6 centimeters, which covers 17 kilometers, 8 kilometers. So it's something that we cannot do with our eyes, with something we cannot do with a single images. And here we can do to have a different kind of information. And then during the week, you will hear a lot about interferometry and SAR and SAR. And now I will, in this basic SAR, mostly the basic one, which is the SAR, polarimetry SAR. And the principal available SAR data that you have here, the list, you have different lists update all the time. And here what Francisco presented, and before. And here I put few things that popular used by people. You have a TerraSAR X, Tandem X, Cosmos Skymet, RadarSat, ALOS, PanSAR, and ALOS 2, and Sentinel-1. And then you can see the access like the one that Francisco showed. The first one is much less restricted, but Sentinel-1 is the first one, free and open access. And for the here is X-band, and C-band, ALOS, PanSAR, N-band, and Sentinel-1 C-band. And you can see also that the there's other SAR like RISAT from India at C-band. There are SARCOM from Argentina at N-band, but those are not that easily accessed, so that a lot of applications were derived from Sentinel-1, for example, because of the accessibility and also the systematic acquisition. And for the polarization, here they are dual polarization here, That's in part the quad pole. Quad pole is usually is a small part, a small piece of land with polarimetric mode. But because it's not global, so it's they are mostly used for research. And the ALOS PanSAR, the same thing for ALOS PanSAR. There are 4 pole polarimetric, but restricted to small surface. And Sentinel-1 just 2 dual pole. And here the SAR mission, then from all that, here with the glance, you can see the history. The history of that is start from 78 with the CSAT satellite from the US, which lasts 3 months. And after that, it's a long time before the SAR mission, like ERS-1 from 92 of ESA, GERS 94 from JAXA, and okay, and then we have ERS-2 here, RadarSat, Envisat, ALOS 2, and here okay, on the C-band and the Sentinel-1 here, and then in the future you will have a nice SAR, maybe at the same time of biomass 2023 and 23, with biomass at P-band and SAR, and band SAR is at the nice SAR. So with the Sentinel-1 next generation, we will have a lot of SAR on space at the same time. So that meaning that it's a time to really to use the SAR data in operation. And here the SAR, on the SAR, characterized by the frequency band or wavelength. Here, Ka, Ku, X, C, S, N, P. And what is the meaning of on that? I think that there's not much meaning. It starts with the X band because it was during the war, and so the frequency band is a secret, so it's X band. Yeah, and after that, so anything, the first name of somebody or something, and then from the wavelength is a small wavelength, open A1 to here P band up to 100 centimeters. But this is the wavelength of the frequency, radar frequency band. And here is the frequency in gigahertz. The the issue is that at the P band, you don't have all the wavelength or all the frequency band for remote sensing. We found a lot in order to have a small bandwidth of the 6 megahertz in this band, and it's, the P band is from 435 megahertz, and megahertz, only 6 megahertz bandwidth. And for the N band is around 25 centimeters, S band about 10 centimeters, C band is about 5.6 centimeters. It's the wavelength used for remote sensing. So inside all the frequency band. And here is the correspondence between the frequency band, the name, and here the gigahertz, and here in centimeters. And the polarization is what we are about here. It shows you transmit the wave in this direction, propagation direction, and here is the plan, the transfer plan, and here you have electric field, magnetic field. So follow the electric field, E arrow. And so the way going that side, like this, and the trajectory of the electric field. And so the polarization could have something in space like this, but then in remote sensing, we talk about horizontal polarization or vertical polarization. This is here the horizontal, the wave go that like this, and vertical like this, and to look at the Earth. And if something easier to, I found something easier to find, it's like we transmit here the radar antenna. Have a vertical filter here for VV, transmit the wave, and just the vertical wave go to the Earth, and then to receive also the vertical wave go back, and the same thing for a horizontal filter here, just here, go to the Earth and going back. And so it's the notion of vertical or horizontal is to refer to the Earth's surface, which is assumed to be horizontal. Okay, so it's not physics, but it's the assumption of the reference, which is horizontal. So the radar scattering. So you see that the backscatter incidence, the incidence electric field going to hit the trees and then go back, the backscatter electric field here, and the amplitude, the phase, and the polarization of ES, they are all modified with respect to EI. Because of this target, change the amplitude of the wave, change the phase, and change the polarization as well. And the basic measurement made by a SAR is called the S, the matrix S, amplitude and phase. It is a complex image, and the type of image, A is the amplitude image, A square is the intensity image, and the phase of a single image is not exploitable. You need at least two images in order to calculate the phase difference between two objects. The radar cross-section. Here, the formula is like in physics. Here, the radar cross-section PQ for the polarization, S is the scattering matrix, and here is the equal to PS is the power scattered by the target. Usually the radar people, they use the power. The physicists use intensity or amplitude, and so, but they are equivalent. And PI is the incidence power, and here is since it's distributed over the whole surface, so there's a 4 pi R2, and it's we use to call it radar cross section. But in the remote sensing, you don't have just an object for the radar cross section, but you have a distributed target. So each resolution cell may contain many scatterers, and the phase varies rapidly with the position of the scatterer inside the resolution cell. And so there's another definition, is the differential backscattering coefficient, sigma 0, is this one, you have seen the radar cross-section divided by the area of the illuminated surface, over which you can consider that the phase remain constant, is the illuminated surface. So this is the formula for the radar backscattering coefficient. And you have to distinguish the slant range and the curve range. The slant range is the part that is here in the slant direction, the side direction, and here, okay, here near range, far range, and if you want to look at this part here, A1 on the graph, you end up with something A2 here is quite smaller because it's on the slant range, and or the B1 become B2, and so the slant range, the same thing, but it's more compressed. And if you transform it into curve range, you have the geometry of the graph. So that all this thing you find in all the textbooks and on the data, the book on SAR data, polarimetry, etc. The list is very long, but before it was radar was used by military, so it's a lot of objects studied by radar. And since the last 20 years, more work on the natural surfaces, natural media like forest, geology, agriculture, ocean, etc. So the second one is the statistic properties of SAR image. Here, when you see a SAR image, one single SAR image, one polarization. Here is a C-band HH polarization. So then you cannot understand the image, the pixel. You have the number in the pixel, and one of the reason is the pixel is affected by speckle noise. Okay. And now the same image after speckle filtering. It's much better because you remove all the noise. Now you see on the road, the aquaculture center, rice field, etc. And then here, I show here two image HH and VV together without filter and with filtering. And here you can see that you start to understand more the images. I can see that this is a rice field, and this is aquaculture because of the water is dark here, and rice field because of the two polarization are different. Because of the rice plant is quite vertical and growing over the water. And see here the road, etc., villages, etc. So we start to understand the image. And so the first thing to do is to remove the speckle. And the speckle, the origin of speckle, when you look at the surface like this, like a fin, to the pixel number 1, 2, 3, 4. 4 pixels with similar aspect or similar name, or like a wheat field, okay, or a forest. And then you have here the many scatterers in the field, and the scatterers are also random. And here you can have here the elementary contribution of each of the scatterers go here, 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 randomly. And at the end, this part, this pixel number 1 here, have a sum, a coherent sum, so some coherent meaning with the face, which is a high. And so the pixel 1 is seen as a bright pixel. In contrast, the pixel number 4 here, you have also the way to go here, 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 to hit one scatterers, go to another, and here is the sum, the coherent sum is small, and so it's the low backscatter, or dark value here, dark value here, so number 4. But they have the same kind of physical characteristic. And here we say that the speckle noise before speckle, after speckle filtering, when we reduce the noise, you can better interpret the image, and you can also doing the retrieval or classification, because it's not convenient if you go to a small field here and there's a value very low or very high inside a homogeneous area. And here is somehow some kind of smoothing. And here, when you do the speckle filtering, and then you start to analyze the image, and then now it's with two polarization or different date, and then you can interpret this. And this one is the same date of the same kind of the radar, but at different date. Then you can see here different plantation logging and different change in the field, etc. So this is you remove the speckle first, and the statistics of speckle. Here you have the two objects, one red and the other one blue. One is some dark object here, minus 14 at the value, and here the brighter object, minus 7 dB, and with the mean value somewhere here, And then when you have those distribution like this, you have a very large distribution of the brighter value and the brighter pixel, and then there's a lot of overlap between the two, and because of the noise is acting as a multiplicative noise. And so here the speckle add to the physical content of the SAR backscatter by adding a multiplicative noise. For the intensity image, it's a gamma distribution, and amplitude image is the Rayleigh distribution. And then the next one show better. Then this the gamma distribution for the intensity. Here I take the blue one. Here the blue one is this one at the beginning, and if we somehow increase the number of looks. The number of looks is the number equivalent number of looks is the number that that quantify how the noise can be reduced when you average it. And for example, the simple case, if two image, two pixels not related together, and you take the mean value of the two, so you can increase the number of looks. It's like equivalent of 2 looks instead of 1, for example. If the number of looks is equivalent to a window size, equivalent to the number of images and so on. And this one here, the number of looks equal to 1, it's a distribution like this, equal to 2 like this, and it's come narrower and narrower. And if you have 64 images here, and it become completely narrow compared to the previous, to the initial one. So the variance of the intensity is the value divided by L, the variance divided by the number of looks. And so it's reduce the distribution, and so that you can use them for discriminate them easily. Then this is an example, an image of SAR. 2 pieces here, blue and yellow is their own forest, and the yellow and here the blue one before filtering and after filtering, and here the yellow one before and after filtering, and here the number of look that we use 20 number of look is about taking many images. And for example, a simple case, you take the 20 image, you have a number equivalent to 20, but minus 1, there's a formula for that. And then here is the 4 look, 20 looks, and then you make it narrow. If you take it very large, and if the area is homogeneous, and then you approach something like a Gaussian. And so if I separate those two things here, if I take the original distribution, they are overlapping. But if I take the narrow one, they are less overlap, because the mean is preserved by this filtering, minus 14.7 minus 11.8, but the distribution is narrower. So this is like the thing that you used to do with filtering, any filtering. But with the radar, you know about the distribution of the noise. So this is convenient to have a very good way to filter. And here the intensity is the scene reflectivity, and V is the spectral noise, so the multiplicative formula. So the scene reflectivity is what we want to measure, and the N is the number of look. And okay, the spectral filtering consists in assessing sigma from I. Sigma here, sigma is the one we want to measure, and by reducing the variance of I, and therefore increasing the equivalent number of looks. And there's a different way to do that. There's a frequency filtering, spectron filtering during SAR processing. Okay, in the SAR processing, if you have a wide bandwidth like 60 megahertz, then you can say that adjacent small bandwidth will have something equivalent. The physical properties of the target will not change much with a small bandwidth, like the megahertz, etc. And then you can cut the frequency band into 3 parts, 4 parts, and in order to make it spectrum filtering during the SAR processing. And with the N band, it's okay, it's C band also, but with the P band, it's just 6 megahertz, you cannot do it. Spatial filtering, it's local estimation using moving kernel or window. You have all the field available, and you have them available on the SAR Pro, on the tool that you will use this week. There's a multi-channel filtering applied on multiple image on the same scene. You can apply multipolarization, multi-temporal, or multi-frequency. The condition is that the area that you are looking at is a homogeneous area in the sense of physical sense, and then you look at the distribution of those areas, and the location of the pixel in the distribution is because of the spectrum. And this multi-image filtering is something very powerful. Here, on the stack of input image, multiple image, so we use Sentinel-1, for example, multiple Sentinel-1, put the filter here, and the output are the stack of images, filter images, and it's preserved radiometry unbiased. So here for a pixel of the homogeneous area, in homogeneous area, the mean value I1 equal to J1. There's no change in the value of the mean value of homogeneous area, but the variance here is reduced. Okay, so that there are also textbook. There's a lot of things about those SAR image properties. Then you can make use of that when you will want to go to detail. Now the second thing is the third thing here, physical content of the SAR data. We talk about scattering mechanisms. The backscatter signal results from surface scattering, volume scattering, and multiple surface volume scattering. Well, like interaction. If there's two things, we say double bars. And the relative importance of this contribution depend on geometric and dielectric properties of the medium. The medium is the surface and also the volume of the earth, for example, vegetation, snow, soil, etc. But all those of these factors depend on the radar frequency, polarization, and incidence angle. So they are mixing up and quite complex to understand when you want to retrieve some of the target properties. And here the scattering mechanism, the surface scattering, here is the water. The wave cannot penetrate inside the water because the weight is the water molecule, like a screen, acts like a screen to avoid the penetration of the weight inside, and the weight will go to the surface and then back to the radar. And here, where you have a soil or rock, you have some penetration. If you have some penetration, and then you can have the volume scattering. If there's penetration, like a very dry soil will penetrate very deeply inside the medium. Like the question is about p-band penetration in the SAR, in the desert, and the p-band is 7 centimeters wavelength, and it depending on the amount of water in the desert sand, but it could penetrate 7 meters inside, and there will be an experiment with the airborne SAR and p-band SAR to assess the penetration. For the vegetation, you have volume scattering here, surface scattering, but also all kinds of volume surface scattering. It's quite complicated. And for snow, you have volume scattering, penetration here, and surface scattering, and even can penetrate inside the soil for volume scattering. So there's some, when you have you receive the signal, ES, the electric field here, the signal from the target, is a result from different kind of interaction. And the interaction, they are not equivalent. It depends on polarization, incidence angle, and frequency. And then you want to maximize one thing. For example, if you want biomass, you don't want to have the surface scattering, volume surface scattering, which involve the soil parameters like soil moisture, soil roughness that you don't have. And when you have, you want to have here the soil moisture, you don't want to have here it depends on how much volume you have, but you need to integrate the kind of volume in your soil. And then with the vegetation cover again, what kind of element that interact with the wave? Here you have the geometric and structural properties of vegetation and soil. Vegetation, you have the scatterer size, scatterer orientation, and density. And for the soil, you have a soil roughness. Here's very smooth soil, and very rough soil. And you have here the dielectric properties. It's related to the water content of the scatterers, and here, and also the soil moisture. So, in short, the radar wave is sensitive to the amount of water molecule in the vegetation, and but the relationship between the signal, the return signal, to the amount of water molecule that return here depend on the structure of the target, whether it's dense, whether on vertical or random, and it depends on also on the soil roughness and soil moisture. For the surface scattering over the soil, here for the smooth surface or rough surface, the smooth surface tend to go to the direction, specular direction, and the rough surface in own kind of direction. So it's the roughness govern the scattering pattern, and the dielectric constant govern the strength of the backscatter. Okay, the dielectric constant of the media. If you have more water in the media, the soil is wetter, the wave cannot penetrate, so more wave going back to the medium one, and the same for here. And so for the for roughness and dielectric constant is related to soil moisture. And roughness of the surface with respect to the wavelength. So the wavelength, if the roughness is related to the wavelength, if you have a 3 centimeters wavelength, a rough surface seen by the X band can be very smooth surface seen by the N band or by P band. So it's the relative to the wavelength. Oh, okay. So I go here, then we understand more. Application to agriculture. So then there's a statistic scattering over from the soil surface. So the okay, we have seen that the radar backscatter depends on the dielectric and geometry of the target and on the frequency, polarization, incidence angle of the wave. And here there's one of the example. There's multiple models describing the scattering from soil surface. There's a very abundant literature about that. And then here I show something simple to analyze. Here is the sigma 0 backscatter. PP is for 2 polarization, V or H. And here the formula show here some Ks, Kn, and Ks, Kn, cosine of theta. Theta is incidence angle. And here is the Fresnel coefficient, and here is the function related to the correlation length of the surface. Okay, I will extend. This is a model described by, developed by using some assumption, approximation of the properties of the surface for the surface scattering. And here is small perturbation. And in all of the models from soil, many of them, the part that attribute to cross polarization, HV, is assumed to be 0. So no cross polarization. We'll see later. And K is the wave number, theta incidence angle. S is a surface root mean square height, and L is surface autocorrelation length. And alpha, HH or VV, is Fresnel coefficient, and which is related to the incidence angle and also to the dielectric constant of the media, epsilon. And sigma 0 is the backscattering coefficient. So when you go to the scattering from the surface, depend on the roughness defined by correlation length and RMS height and the incidence angle and the dielectric constant of the media. And so for the we did a lot of experiment with agricultural surface roughness in the past. And then here is the seed bed, is very smooth, harrow or plow, and here the root mean square height, mean value, standard deviation, correlation length, standard deviation. And so you can see that usually we say root mean square height seed bed in centimeters, 0.6, 1.6, 2.7. And we mean we measure long profile up in by laser, and we calculate all those parameters, And then we hopefully that there's a repeat measurement by many people. And then we found out that using the same machine for agriculture, we have the same similar value of RMS height and correlation length. Soil dielectric constant. We talk about permittivity or dielectric constant, and it is the concept that the molecule inside the medium, which modify the propagation of the wave inside the medium, and it's for a living medium. It's the molecule that vibrate where you have the excitation by the wave is a water molecule, because the water molecule is like this 105 degrees OHH, and then when under excitement of the wave it's vibrated, and then if it's a very strong excitement like in the microwave oven, and then you have a dissipation of the heat, and then you hit the food. But hopefully with the SAR we don't have that strong excitement. And here the dielectric constant, the real part and imaginary part. Also you can just to give you the notion, the concept, because it's a lot of textbooks about that. And here you it's interesting to see three kinds of sand of soil, and compared to here is a volumetric water content and dielectric constant. The more you have the water, the more you have the dielectric constant is high. And then with the clay, the increase is very low from the beginning, because of the water is inside the phytosilicate layer, cannot move much, and so the increase is very slow, and then the big increase after amount of water is here 20% rich. So it's there's some physical inside. And then when you look at the surface, you have the low backscatter because of dry soil. High backscatter is wet soil because of this is irrigated. But you can have here, this one is the smooth surface, and this one is a high backscatter because of very rough surface. So at the same time, you can have a constant roughness here, for constant moisture, and you have simultaneous effect of roughness and moisture on the radar signal. And so again, if you take one image, it's not useful. But for this, the simple way is to take a time series of data, and you can understand that the water content change at a different speed than the roughness of the surface. And so you can play around the multiple images in order to do the retrieval of soil moisture, for example. And now there's a soil moisture retrieval using ERS, using Sentinel-1. And here, what we did before is, okay, a long time ago, then we have here the fin irrigate in Morocco, and then, but it depends on the roughness of the fin, and it depends only on the correlation length of the fin. So it was considered that it's difficult to retrieve just the soil moisture. And polarization in surface scattering for the smooth surface, we consider no depolarization, no HV/VH. And for the Fresnel reflectivity, you remember the alpha, VV and HH. and the H is higher than the V. It's the, you remember in physics about the booster angle around, but I will not go in detail. But for the rough surface, you have some depolarization. It's go here, go here, go here, and the reflectivity equal H equal RV. So if you have an image of one incident, one frequency, and here the rough surface have a higher backscatter than the smooth surface. And with the vegetation cover, how it goes? Here, the order 0, you go to the attenuated surface scattering, and then simple scattering here, go to this one, go back, volume scattering, and you can have here the multiple surface volume, volume surface, or multiple surface volume surface, etc. And usually we approximate by something simple, sigma 0 for from the radar equal to sigma 0 from soil, vegetation, plus the multiple interaction. And so again, if you want to maximize the vegetation sensitivity or the soil sensitivity, you have to understand the whole pictures. And okay, this one is the volume scattering. Volume scattering can be like this or can be like that, multiple inside the cover. And then when you have the point scatterer, there's no depolarization. It's spheric, isotropic spheric scatterers, no depolarization. It goes from V, you go back V. And here, if anisotropic scatterers, it go V, it can return somehow some H. We say that there's some depolarization. And for multiple scattering, after many interaction with on the canopy elements, and then there's some depolarization. And so for H3 or VH, high backscatter of vegetation canopy compared to the soil. And here is an example that for the colleagues who using opticon data. And here is we compare, we use here opticon image, and here is Sentinel-1, Sentinel-2 equivalent, and they give different pictures of what is going on. Here is the wheat fin, and here the wheat fin here is dark is meaning low backscatter, and whereas in very high here, high NDVI, you may know about that, is normalized differential vegetation index. The higher you have, the vegetation grow biomass, and here the grow vegetation, and here high vegetation index but low backscatter. And we try to understand the whole thing. And there's also a lot of papers, publication about it. And there's two things. We showed just two examples. There's a winter crops with a rapeseed. Rapeseed, you know what it is? Rapeseed is a yellow flower from at the beginning, but when it's ripe, it's some like a bean. Yeah. And for here, the VH, and the ratio. And here, look at VV. In here, I show temperatures and rainfall. Here, it's a very surprising for who cannot understand the physics of this. The rapeseed in red going up with the vegetation curve. and okay, the first block of gray is the sowing period, and the second block of gray is the harvest period. So after that is the soil or other thing. And so here the opticon show the something like NDVI here, NDVI, the increase of the vegetation, both of them, but at the beginning they are different because of the different growth of the plant. And just look at the leaf, and here we look at soil and vegetation. And here the interesting, when the vegetation grow, the width fin decrease. Width fin decrease because of the part, which is the soil, because the width is sparse compared to other crops. And then what you see is the soil attenuated. And the soil attenuated by the vegetation. The more you have the vegetation, the less you have the signal from the radar. And reversely for the rapeseed is quite dense. There's no the soil return is not dominant. It's a vegetation dominant, and so it's increased with the vegetation. And also two things interesting. When you take the ratio of the two, you VH or VV, you reduce the part which is due to the soil, the soil attenuation, and so the width and the rapeseed show the same thing than the opticon. So this is in order to understand the dominant scattering mechanism depend on the vegetation cover, dense, not dense, high, not high, and with water, without water, etc. And here is the other crops in the summer crops, sunflower, etc. And then we can play for those crops. For example, they are quite dense. So the VH volume scattering increase with the growth of the plant, and so it could be used here for the VH could be used for example, crop classification, and all those things can be you can if you understand what happened in for the different crops, and then you can use them different polarization in order to do the crop mapping, for example. And in some places you have just the radar because of the weather is not good. You cannot do it with optical data, and so there's a potential for many things. Okay, now I go to the application of forest. I'm looking at how long. Okay, half an hour. Application to forest and biomass estimation, but Clément did a lot already about the biomass of the mission. Okay, how do the radar see the trees? Here I have an Austrian pine in the south of France, and then at X-band I see the needle only 3 centimeters wavelength. At C-band I see the needle, small branch, and small twig, etc. And the N-band, you start to not to see much the needle, but you see the branch, the twig, the branch. And at P-band, you see bigger branch, you don't see the small needle. And we did an experiment before using VHF, very high frequency, 3 meters frequency. We see just the trunk. Yeah. Okay, so the radar sees the object which is somehow proportional to the size of the wavelength. It's not equivalent to the wavelength. It's not 70 centimeters, but there's some criteria for which kind of scatterers that a radar can see. And for you know about relay scattering, Mie scattering, etc. And the rule of thumb is something like a lambda over 10, 1/10 of the lambda for the relay criteria, but there's other criteria as well. And so if you see here on the needle here, it's obvious that when the tree increases in biomass, and then the number of scatterers will be very high very quickly. So saturation. For the C-band, the same. Saturation, because of the number of scatterers become infinity. And for the N-band, it's a bit better, but there's more needle, more small thing in the trees. So it will saturate a bit later. And for the P-band, the only wavelength that we can have in space. So it's we see a big element, and so saturation much later. In VHF, we didn't see saturation in our forest, for example. And so that's why at the beginning we proposed the P-band, because of the saturation of the wave here put a limitation on the biomass retrieval for example, for tropical forest that can go up to 500 tons per hectare. And so it's, we have to take the lower frequency possible or the higher wavelength possible. And the interaction mechanism, and you have the scatterers contribution here, and the mechanism here, 1, 2, 3, etc. 1 is the crowd scattering, 2 is the trunk crowd scattering, 3 at the trunk, 4 is the multiple, okay, and 5 is attenuated crowd here, go to here, and 6 is a direct crowd scattering. So this is a sketch because of there is a multiple thing everywhere. It can touch the first one, the second tree, and your back, etc. And what are the scatterers contribution? There's a leaf needle, primary branch, secondary branch, high order branch, trunk, etc. And for the C-band, you can have just 1 or 2, 3 mechanism, and scatterer contribution is, for example, for the C-band, leaf needle and small tick, and etc. And then I show this here. For C-band, you see just attenuate the crowd, direct crowd scattering, and direct the soil here, and the leaf needle and small tick. And so saturation is quite fast. Okay, and now can you have a closer look? And this interesting because it was the beginning of the P-band biomass mission. Yeah, and here the team working with us in MIT doing the radiative transfer modeling with us about that. This paper here, and then at the P-band HH, and here look at this. This is the total that you receive from the radar. Here the trunk crowd. Here the crowd is canopy, a crowd. Here is the crowd. Crowd is the volume and the canopy, the volume. And it's HH, HV, the crowd, and here is the crowd, the interaction. VV, the crowd, here, trunk crowd, and the crowd. Okay, what does it mean? if I take this one, the HH, I take this one, it looks like it's saturated quite fast, but this is a simulation. Yeah. And when you look at just the cloud, the cloud, the thing that touches the canopy, the increase is not saturated. The cloud is not saturated, but it's the total is attenuated by the interaction, cloud, and we don't talk about the open air cloud. And this is HH. HV is less because the other are smaller, because of the simulation, anything that touches the cloud is HV is quite small. So just the cloud. And here the VV, it's okay, the cloud, but at the beginning, the cloud is also dominant, and so in total there's no sensitivity. So that we say that okay, the HV could be used, but just in case, we have to do anything to remove the effect of the cloud. Okay, so this also have some impact after many years. Okay, so this is the simulation on a forest in France. That's 3 papers here, long time. And okay, the change in dominant mechanism also is just illustrate the double mouth here. It's here the Varsia dry. It's in Brazil. Douglas can know what it is. And here is the SAR image and HH. Okay, you see something, but when it's wet, and then this double mouth increase, and then suddenly you see very bright return here, so brighter than the forest outside. So this is the change in dominant mechanism can happen with environment condition. And for the forest structure, and if you see that the boreal versus tropical rainforest, the structure are not similar at all. And here you can have a lot of open mouth, you can have penetration in the ground, and here you could have something, but it's very complicated. And okay, but here your eyes are refrained by the leaf, but for the radar, for the P-band radar, the leaf is not that important. So it's and this one is the another simulation by Sachi team of the boreal forest here. Boreal forest, and you see the surface scattering, the cloud scattering, the stem surface. And here, okay, there's a tree curve here going up, and the soil is a tree curve going down, the effect of the soil. And so if you have the soil return at low biomass, and then here you have a curve which has not much sensitivity, and that's why you observe with ALOS data here, and we can see that after 100 tons per hectare, the N-band saturated. If you just use this way to do the return, to do the retrieval. Something about the dielectric constant. Dielectric constant, the number of water molecule inside the trees. So here is the team from Bordeaux doing the dielectric constant of wood, but with the wood sample. So it's that wood, and it's just to tell you that the more you have water, and the dielectric constant increase, and it's a spruce, pine, and beech, and two fin, the measurement parallel, electric fin parallel to the fiber, and here the parallel, perpendicular to the fiber, because the wood has a fiber. And so it's sometimes you see that they increase, but they have a different for the spruce than the beech and the pine. And here, the electric constant of living wood. The previous example showed the measurement in laboratory with the sample of wood that people cut, dry, and put the water. And here is the measurement on the trees that Clément did it sometime, and now we are doing that in French Guiana. And here is the it's 2-day measurement of the electric constant for PCR ABS. So it's a Christmas tree, and here you have at the bottom 0.6 meters in the trunk, 1.7 meters, 3.9 meters, 5.2 meters. And then you can see that the electric constant have a cycle, Leonard cycle. And so it changed from the top to bottom. And so that it's because of here they compare with the vapor pressure deficit of water. We can also measure it as a function of the silent sap going up and down, silent dielectric constant in here, going up and down in the trees according to the time of the day. For example, here, the maximum dielectric constant is about 12 o'clock, and the minimum here, minimum is the midnight or something, you see, in the Leonard cycle. And that's what we are doing with the campaign in the tropical forest. It's in French Guiana, Tropiscat. Okay, so we do the fully polarimetric to have vertical resolution capability every 15 minutes over a time span of 1 year, in order to assess to the vertical structure of temporal decorrelation. And the first thing is to have a temporal decorrelation between the measurement, because of the satellite repeat pass is maybe 3 days, or it can go back 17 days, 1 month, etc. And so for each time, what we have is this one. You see the measurement of the forest, and then we see the concentration here somewhere, and it go up and go down during the day, and it's something like this. Is I have to make it better. Yeah, and here the center of mass as a function of time from midnight. Okay, so from those distribution, we calculate that the maximum, the minimum, maximum of the distribution. The question is the center of mass, and then here we see that the center of mass going up and down in time lapse in hour 0 from midnight. And okay, every day it go up and down, and it change according to the polarization. And so it's something to know with the trees itself, not the radar. And here in blow up of this, 0 is midnight, midnight, and then at 6 o'clock, here see that the center of mass is here, but at it start to go down from 7 o'clock, and minimum here at 13:15 p.m. and then go up again at 22, 23 hours. Okay, and the amplitude is inside the forest, 1.5 meters inside a forest. So meaning that amplitude is higher with the blue one, which is VV, than the, oh no, the blue one is the HV is higher than the red one is VH here, VH and HH and VV. And okay, and so we can detect this Leonard HH, VV, and HV of the signal over a tropical forest where nothing changed. And so it's very important because here you see that in dB, if you take here the intensity, there's at least 1 dB of difference during the day. And then one difference during the day, the night orbit and morning orbit can have 1 dB or half a dB difference. And half a dB, since the sensitivity is reduced at high biomass, and then it can be important. So we have to know, to understand about that before the retrieval. Also, we have to define with all the data we have how much, what is the orbit, the best orbit, and then because of this one, we take the 6 o'clock in the morning, is the reference local time in order to have stability of the signal. Okay, the same thing in Reminstorp in Sweden, given by Lars Olander, Montate. And here you have the same setup in the tropic boreal forest. And they look at PN and C-band data, like us now in French Guiana. Okay, and here what Clément showed already, but I see here the tree curve. The total is black, the crown is yellow, and the canopy is green. And so you can see here VH, the crown contribution is lower than the two others. And here HH, the crown contribution equal to the vegetation contribution. You can see also variation here, big variation in winter. And here the range, the variation in winter, because of the free fall, you can have a 12 dB of difference between the here, and you can see that in this case the change is mostly for the canopy. The soil is stable. Okay, and okay, and now a bit about forest biomass. It's as say Clément, is a key element in the carbon cycle. It is essential climate variable of the ESA CCI biomass. CCI is a climate change initiative. So it's a biomass consists of approximately 50% carbon, and forests account for 70-90% of the terrestrial biomass, and the majority located in the tropics. And the problem is that the forest biomass stocks and their change remain poorly quantified, despite a lot of effort using existing satellite data. And here is how researchers are doing the biomass measurement. Okay, so this is again a forest, a major carbon sink, but can be carbon source when it's burned. Here, there's the source of carbon. The International Convention and National Determination on the Forest aim at increased carbon sequestration, reduce the emission. And for that, we need to quantify carbon losses again for the carbon cycle. And for the biomass, as you have already seen that there's some kind of saturation. The P band here, N band here is the simulation using the model and describing the forest like this. And then you can see that saturation is earlier at N-band than at P-band. And this here is sugar. He compared two results here, N-band HV by such and such, and here by me in the past. And so we can see here the saturation is quite early. Here is not that early, but the sensitivity here is quite low. I mean that there's a few fraction of dB from here to here. It's a 300 ton per hectare. Now we go to 500 ton per hectare. We need to do something to increase that. Now again, this one is how to, because of the understanding of that we say, okay, the data must be processed to retain only the volume component of the forest canopy. So we have the measurement, we have the different measurement mode, and now we will have the data and how we will play with that in order to cancel the contribution of the crowd. Again, we take the Ponsa, Poninsa, and Tomosa. So this one, we have both the cow vegetation and the vegetation and the interaction between the two contributions. And this one, we have the height in addition here. And this one, we can have a different layer inside the forest. So the way is with Ponsa, we cannot do much, but with this one and with this one, we can find ways to reduce to take away the crowd contribution. And at the beginning of maybe less than 10 years ago, we use Tomosa in order to the Tomosa that you have seen it with Plymouth. Here is the flux tower, and the top of the flux tower here we can see at 45 meters. And here is the high backscatter intensity because of the tower, and then we can do it with any of the places in order to have different layer of the forest. And here, boreal forest and tropical forest, and using this, we understand more the mechanism. Here is the HV in boreal forest is quite low. This is the height, and this is the we call it tomogram in slant range, and the white is the leader canopy at the same time. We make a transect. And here is the B-band in tropical forest. And you can see that it's different. Here you have the dominant at the crown level here, except here a bit, most of the time is dominant by the crown level. And here in the tropical, you have a different height. The backscatter come from the different height of the canopy, and so we understand more. And then we say that we have to find okay. And this is to compare with different polarization. Okay, so HH, HV, VV. On that you will have, I think, in Tomo SAR, and the last day by Laurent and Stefano. And here it's just we simulate the 6 megahertz bandwidth of biomass, and we degrade the tomogram. And here we can see that it's the domination here, VV, HV, and HH. And then we try to, this one. Okay. Then from different layer of the forest, the idea is we have to look at a layer where we don't have the effect of the ground, but the biomass of this layer must be related to the AGB. AGB is about cow biomass. Why the biomass of this layer is related to the biomass of the total area. And so we use the model describing the growth of the tropical forest. And then we see that this part, 20-40 meters layer containing big crowd, big bunches and so on, are well related to about cow biomass. And here we explain this in the paper by Stefano last year. And here, Clément showed what happened in Parakou at the ground level. What we see, the image, the SAR image, and ground level, and ground level plus 15 meters at 30 meters, 30 meters. And here is another site, Nourag, the same thing. And then we calculate here the correlation with biomass, and here for the ground level, here the total ground level, 15 meters and 30 meters. 30 meters, suddenly it's no crowd effect. So there's a different paper about that by Ho Tong Minh Dinh. Okay, so we use this and we test it. We use data from one side to apply to the other, and then we have a map of the forest. Here is 50 meters up to about 500 tons per hectare. And here we go beyond that to have a site in the tropic SAR campaign in Africa, different site, and here we compare different sites in different days. And so we think that this part is quite robust. And then the other way to isolate the volume by crowd concentration, here the HH-VV phase difference at ground level and at the 30 meters high. And you can see here the ground level, it's the forest with different value of biomass inside, but you see it's quite dominated by the crowd topography also, the drainage pattern, etc. But then you go to 30 meters, you don't see the crowd contribution. Okay, and so for the biomass estimation with the biomass mission, we have strong evidence that the volume layer 25-35 meters above the crowd in tropical forest is strongly correlated with the total AGB, and development of method for crowd concentration using tomography or pulsar to isolate the volume scattering, and to develop an approach to solve the volume scattering equation that minimizes the need for reference data. Because if the method is robust enough, then the need to have data scatter everywhere is less demanding. And I think that I make a summary at the end. And I have given introduction of SAR remote sensing with some focus on agriculture and forest. And it is essential to understand the statistical properties of SAR images and the physical content of the SAR data to interpret and to analyze the data, and to develop retrieval and mapping algorithms. If you don't understand, you can have one reason, one example, and then it cannot apply to elsewhere, etc. So you will have lectures and training on advanced SAR, polarimetry, Bonin SAR, and TomoSAR, and in the following session this week. So normally this one is supposed to give you some basic thing that you can understand just by hand, understand what is what, and then in the detail will be given in the following lectures. So thank you very much.